we got the EMF there. The flux rule is basically an experimental rule. Michael Faraday did his experiments. He actually drew painstakingly many flux diagrams. What are flux diagrams? You draw field lines. All the total number of fields together can be approximately termed as flux, though the mathematical definition will be different. Broadly speaking, the total number of lines in a magnetic field you can call as flux. So when he was doing experiments by moving magnets into the coils or doing motion EMF experiments, whatever, in all his experiments he was drawing the flux lines practically, field lines practically, and he concluded whatever is happening inside, first let us not worry about it. In every case, what is invariably happening is that flux through the circuit is changing. So that's what he could notice. So when flux changes through a circuit, that induces EMF. Here we talked two things. There were two things there. The flux through the area enclosed by the rod and the loop is changing because B is changing with time, but that is dB by dt. But it is also changing because of the motion of the rod. As the rod is moving forward, the area enclosed by the rod and the pie-shaped conductor is changing, therefore flux is changing. But remember, I would want to separate this motion EMF from the dB by dt anyway. That will come soon. But if you close that circuit there with the rod, even there we can happily, conveniently take that flux is changing through the area enclosed by the rod and the loop. So the area is, the flux is changing because of B changing, because of A changing. But what is happening inside? This is one very, very important thing. What must be happening inside? See, if the current is going in the circuit, EMF is formed and current is going, electrons must be moving. Until then we knew that cells, chemical cells produce what you call electron flow in the metal conductors, we knew. Here there is no cell there, there is no electrolytic cell or anything like that here, but there is a current flowing. So what is happening? That's what you mean by the physics. You do an experiment and explain why this is happening, then it becomes a knowledge. Like you do many experiments and see a commonality in the experiments and generalize the result and frame a theory. Theory means, remember, it's a mathematical theory, not just talking about it. Anybody can talk anything. Unless you convert that talk into mathematics, it won't become physics. So once the theory is framed, you can do more experiments, improvise experiments, and apply it in industry, apply it in every possible scenario later. Now let us try to understand, as the flux is changing, what's happening inside. Remember, changing flux is pushing electrons is not the idea. Okay, so there must be a force acting on the electrons for the electrons to move. Alright, that's the basic physics we need to apply. We are still working with Newtonian dynamics, you can say, for a while. That is, electrons' motion has to be understood in terms of their being pushed by forces. Right? So there are two things here, A dB by dt. We'll take that first. In fact, these two things can happen separately. That in the problem, you could have been given only A dB by dt. That means the rod could have been fixed and the magnetic field could have been changed, or the magnetic field could have been kept constant and the rod could have been moved. But this particular problem has these two things put into one. Therefore we chose that problem to explain some basic principles of physics. Here, the principle of electromagnetic induction. Now the first part will take A dB by dt. Time-varying magnetic fields in space produce non-conservative electric fields in that region of space. This is what Faraday introduced. In a region of space, if there is a magnetic field changing with time, along with it there exists one electric field in that region. Until then we knew when a current is flowing through a wire, moving charges are there, there's a magnetic field around the wire, we know. But now what are we saying? In a room, for example, say the roof is North Pole and this floor is South Pole, and due to some reason that strength of the North Pole and South Pole is changing, so the magnetic field in the room is changing with time. What Faraday says is, this time varying magnetic field, it has one electric field associated with it, and in such field you put a conducting loop, a metal loop. That field will act upon the electrons inside the loop, and that is the reason for the current flow in the loop. That's what you can say. If you have a bar magnet moving into a coil and you put a galvanometer here, this is the flux magnetic field lines. When you push it towards the plane of the coil, the number of flux lines going to the number of field lines going to the area of the metal conductor are changing, and you see that there's a current flowing. Flux change is making the current flow is the observation. But now what we say is, this is a time varying magnetic field now, isn't it so? At a particular region, B is not remaining constant, that's changing with time. So what Faraday says is, in this region there is electric field. Remember, this electric field will be there whether you place this conductor or not. But when you place it here, this electric field applies force on the electrons which are stationary here. Basically, as a whole, they are not moving, they are not forming a current. Electrons are in random motion, the loop, all right, but the net motion of the electrons is zero. So on those stationary electrons, this electric field formed by time varying magnetic field is applying force, and the electrons are moving, is Faraday's explanation. So the first part is that we need to remember, time varying magnetic fields in space produce a non-conservative electric field, of course. That's very important. The electric field produced by electric charges like this are conservative fields. In such fields, the work done to move a charge in a closed path will be zero. But here, the work done cannot be zero, isn't it? So when current flows, some heat is lost. So work is not zero here. Therefore, the field formed must be non-conservative. See, the logic is like this. The stationary electrons cannot experience a force because of the magnetic field. That's one thing we should understand. And only way the electrons in the wire can move is because of the electric field. The electrons in the loop are stationary. So how at all these stationary electrons can move? They can move if there is electric field. So that's where Faraday told. In fact, they were actually looking for it, because moving charges are forming magnetic fields, isn't so? In other words, electric fields are producing magnetic fields, so magnetic fields must be producing electric fields. So the idea, they were looking for it, and this offered the required proof for them to say that yes, when magnetic fields are changing in a region of space, they should be producing electric fields, and that electric field should be driving the electrons in the wire, and that shows as current. We've talked, but how this time, now we can see how this time varying magnetic fields can be formed. Like this, a bar magnet may be moved. When a bar magnet moves like this, in this region, field will be changing with time. In a similar way, you change the current in a coil. When you change the current in the coil, magnetic field surrounding it also changes with time. So these are the most two popular examples based on which problem setters will be framing problems. What we need to understand is that the magnetic field should change with the time and space. That creates one electric field. And you place in that electric field one conductor which is closed, current flows. Remember, even if you put an open conductor also, EMF will be formed, current doesn't flow. Potential difference, don't misunderstand it to be the potential difference formed previously, but it is a potential difference related to the non-conservative field. So when you close the circuit, current flows. So Faraday beautifully connected his experimental observation that changing flux through a circuit produces EMF to his theoretical proposition that the flux change actually is not the direct thing which is acting upon the electrons, but it is a time varying magnetic field producing a non-conservative EMF, a non-conservative electric field, and that electric field is driving the electrons in the wire. So how to connect these two things we can see. This thing is a time varying magnetic field. I showed it by not so parallel a group of lines here. When I show parallel lines, it is supposed to be uniform. That is, field is going to be same all over. Now if I show a field like this, it is a non-uniform magnetic field, which is non-uniform because it is changing with time. Now in this you can imagine one loop. This is not the conducting loop I put. In fact, this loop can be made of any shape, zigzag shape you can imagine. That's not a big deal. It's only imaginary loop. So what Faraday says is, because of this time varying magnetic field, there is an electric field in this loop, and that electric field you circulate it over an imaginary loop. That electric field is circulated like this. That means the field is there everywhere. We write the integral E dot dl of this. Look, E dot dl is nothing but EMF only. E is force by charge. So work done per unit positive charge to move it in a closed loop is what you call EMF. So this EMF should be equal to the rate of change of the negative rate of change of flux passing through a surface which is bounded by our loop. I repeat, the work done by this non-conservative field in a closed loop is not zero. If it is the electrostatic field, if it is electric field formed by charges, electric charges, work done E dot dl will be zero. Here it's not zero, there is a value for it. But how much is equal to? Experimentally, it is equal to the rate of change of flux through the area bounded by our imaginary loop. So that's how we beautifully connected his experimental result of d phi by dt minus d phi by dt to the theoretically predicted non-conservative electric fields formed as a result of the time varying magnetic fields.